Good. Hi, thank you for the introduction. My name is Oleg, and I will share my screen in a second, and we'll probably start. Somebody else is sharing screen. Should I take over?
Just go on, share it. You will take it over.
Yeah, very good, very good. Right.
Cool, I see it.
So, excellent, very, very good. Right, let's go into the slides quickly and start with the session. Right, so my name is Oleg Šelajev. I'm very happy to be here. It's always a pleasure to talk to people, and just absolutely love when people learn more about GraalVM. So in this session, we're going to talk about the microservices and what GraalVM offers for the microservices creation. Specifically, one of the large things that are interesting for this is the GraalVM native image technology. So we're going to get there. And then I want to show you a couple of examples of a sample application and how I built the native images and how also I use some more advanced features to make them even better and faster and more appropriate for your workloads. But before we start with a little bit of introduction. So I work as a developer advocate at Oracle Labs on the GraalVM team. And if you have any questions and you cannot find me here because there is no time or anything, you can find me on the internet. I go by @Šelajev almost universally. You can tweet at me, you can email me, you can find me on GitHub, and so on. Before we go into the actual content part of the session, please note that this is a technical presentation, so do not make any foregoing business decisions based on the contents of this, and also that the GraalVM native image is available under the early adopter status, so be mindful of that. GraalVM in general is a high-performance polyglot embeddable runtime for your applications that can run programs in different languages. So we have a bunch of languages that are currently supported and can run on GraalVM. So GraalVM bases on the JDK. So it's very natural that you can do all the JVM languages, right? So we have support for Java, Scala, Kotlin, and so on, but also a number of others. And this is a very exciting project, and it's a very ambitious project that can transform the ecosystem in a very revolutionary manner. For Java developers, the main value proposition of GraalVM are three pillars, so to speak. One is the JIT compiler, which is probably the most sophisticated and state-of-the-art JIT compiler for Java workloads currently available for people. So you can run your applications normally, and they will eventually run faster than anything else. Another one is the native image technology, which features application of the same compiler, right? It's the same GraalVM compiler, but it is used as an ahead-of-time compilation mode. So it can transform your application and produce the native binary for the target platform. So you can package it without a dependency on the JVM, and it will be a standalone application, and it will feature different performance profile compared to running your applications normally. And this is a very interesting technology, specifically for deploying into clouds and using in different microservices contexts. And the third value proposition is the polyglot virtual machine. What it means that you don't have to, right? Because very many people are confused about this. You don't have to, but you might use and build a system where different components are built using different languages. So for example, you can enhance your application with some JavaScript logic, which could be very useful if you want to, for example, render some JavaScript application on the server side. Or you can mix and match the system and use some modules from Python, for example, for machine learning, or from R for data science. So it offers you different possibilities. It opens the ecosystems of other languages to your Java applications, and it also offers your Java libraries, the code that you write and produce, to the communities of those other languages. So you can use your Java libraries inside your Node.js application, for example, which is very useful. those Node.js developers and JavaScript developers are very happy to learn that they can now have your null pointer exceptions as well, not just their own problems, but typical Java problems as well. Right, so that was a joke. You give them very good and very hardworking and beautiful and efficient code. For Java applications, right, your Java applications, you can run them normally in two different ways, right? So there's the state-of-the-art JIT, and there is this ahead-of-time compilation mode. And what the beauty of that is that you can take the same application and you can run them with a JIT or in the ahead-of-time compile mode. So that means there is an option. GraalVM gives you an option. It doesn't force you to use any of those, right? But you can choose whichever you want to use. You can use the JIT, and then you run your application normally using Java command line, right? So you do the Java utility -jar my jar file, and it will run normally. It will start the hotspot VM, Java hotspot VM from the OpenJDK project, or from like Oracle JDK builds if you use GraalVM Enterprise Edition. But it's a normal Java hotspot VM. It will do everything that the Java hotspot VM should do. It will locate classes. It will start processing them. It will verify them. It will start executing them. Eventually, some code will get to the higher compilation levels, and then it will become JIT compiled, right? And the top, absolutely the most optimizing JIT compiler in the GraalVM builds is the GraalVM compiler. So the code that runs the most and needs optimizing the most will be passed to that by the JVM, and then the compiler will optimize that, and it will run beautifully. So that is on the left, that is the JIT mode. And then with ahead-of-time compilation mode, there is a different life cycle. So you feed your application classes to the native image utility, and then it will compile them ahead of time. It will initialize some classes. It will process the application. It will remove all unnecessary code that will never be run in the application, and then it will produce the binary. And then you have to run that binary. So there are two clear steps, which is your application lifecycle, so to speak, is separated into two steps: the building of the native image and running the native image. So, and that gives you a lot of benefits. When you run in the JIT mode, and I want to emphasize that, and specifically in the session about the performance and efficiency, because very often people in the community and developers that talk to me, like they say that GraalVM is all about this ahead-of-time compilation, right? And then from that they have kind of, they're confused because they limit themselves to just this one ahead-of-time compilation mode. But what I want to say, like running Java applications normally with the JIT is a very important use case, and GraalVM excels at that, and it gives you an option. So you have to just remember that. And when you run your Java application normally with the JIT, this is the one architecture picture that how the GraalVM components kind of like lay over the runtime there. So it starts the hotspot VM. It plugs in the GraalVM JIT compiler. It can run with those two bottom layers. It can run the Java JVM language workloads. And then it adds a Truffle framework, which is a framework for creating managed languages on top of GraalVM. And this is a Java application, right? So that's why it's on the same level as other Java applications there. So it gives you API to create languages if you want. And those could be like fully featured programming languages. Like, for example, we have support for Ruby, R, JavaScript, WebAssembly, Python. There is a community project for GraalSqueak for Smalltalk. There is an LVM bitcode interpreter through which we can run native languages like C and C++. But it also can run like smaller languages. For example, there is a regular expression engine, or there could be like some small language DSL for your particular task. So it's a very generic framework for creating languages as well. So with all that, we can run a number of things, right? We can run everything that goes through bytecode. We can run applications written in those other languages. We can run Doom because it's a native application. If you compile it through LVM bitcode, you can run it on GraalVM. Yes, and this is like GraalVM compiler. Here you can see that it has to power actually quite a bit of different applications, and you can assume that interpreters for those languages are very dynamic because languages they're represented there are very dynamic. So the compiler needs to be very sophisticated to produce good results in those languages, right? Because at runtime you can imagine that there is an interpreter for, say, JavaScript, and then it will take the JavaScript program, and then it will start executing that, and then it will start compiling that at runtime in a like just-in-time compilation mode to the machine code. So it will take the complexity of your JavaScript program, and it will take the complexity of the interpreter. It will mesh them together, right? It will sort of inline. You can think about that as inlining your JavaScript program into your Java interpreter for JavaScript. And then that complex structure will be passed to the JIT compiler. And JIT compiler needs to see through that and optimize that. And that's why, and well, GraalVM compiler produces really good results on those, right? So it produces really good results on those very complex and very dynamic programs. And that's why, like, partly it's so powerful. Because if it produces good results on those complex things, it should also produce good results on simpler things. That is just very natural because it has the power for that. And yes, and that is one of the, like, it's a little bit of a backwards argument, but it actually makes a lot of sense if you think about that. When you excel at complex things, you naturally are good at simpler things that are part of those complex things as well. And you can see that all for yourself very simply. You can download GraalVM, then you just can untar, unzip the package, put it on the path, and use your GraalVM as your Java, as your JDK normally. Currently, we provide builds for Java 8 and Java 11 based distributions. So if there is a chat facility here, I would absolutely love you. I will absolutely love to hear from you which versions of Java you normally use in production the most. If you have 8 or 11, then you can use GraalVM out of the box. Just download, unpack it. You can, it's a compatible JDK, and you can replace your path, and you can run your Java on GraalVM and measure the results. And I would absolutely be thrilled to hear about your experiences. Why is this important? Because performance is money. The more hardware you need to run to support your application workloads, the more money you actually have to pay for that. It's very similar, and it's very clear on the large scale, right? If you have to build like 5 data centers, for example, to support the workloads, and then suddenly you can have a runtime which is 20% faster, then suddenly it happens that you need to build only 4 data centers. So think about that. One company that uses GraalVM technology is Twitter. So Twitter is using the GraalVM compiler to run their Scala microservices. And they're very happy about that. There were a number of sessions at the various conferences, how they use the GraalVM compiler and how they get the results. Chris Challenger is one of the Twitter VM engineering group people who talks about that experience and shares that expertise with the community. So you can look him up and those session up and see that. But they get really good results, and they are happy using the compiler there to speed up their workloads. Oracle Cloud Infrastructure telemetry service migrated, I think it actually was last year now. 2020 was really fast paced, so I think this was last year. Migrated the telemetry service, and they see better peak performance. They see less time spent in garbage collection, and the migration was seamless, right? So they just like a drop-in replacement for JDK. And we know that GraalVM shows really good numbers for your Java workloads. So if you run your Java applications, right, the same way, like without doing anything else, what you can do, you can switch your runtime for GraalVM, and you can see whether it gives you benefits in the performance. So which is very important because you can save money like that. And we know that because we run tons of benchmarks. You can see here the snapshot of the Renaissance benchmark suite, which consists of different from benchmarks from different applications and libraries. right, in the modern ecosystem. So those, you can recognize the normal and kind of things that we're using every day now. So there are, on the right, there are some reactors API, some reactive extensions, Arts, Scrabble. There is some Scala. There is some Neo4j, which is a graph database, of course. There is some compilation tasks happening. There is some akka, which is an actor-based. And those tasks, those benchmarks, they feature different parts. So some of them are computationally intensive, some of them are memory intensive, some of them are parallelizable. So they feature and stress different parts of the processing. And GraalVM shows really good results on those. So you can see that, you can try that. You can try other benchmarks as well. We run a ton of them. So there is no reason not to use GraalVM for your JDK, which you should at least consider, because it can make applications more efficient and faster. But now we get to the second part. We get to the cloud, and the cloud is different. Cloud is where we don't run our applications normally as we usually do those on well, also cloud, but like large servers, right? Because if you run your applications normally, if you give it enough time to warm up, if you give it enough time to hit the top tier JIT, then yes, of course, the better JIT will give you performance boost. But in the cloud, very often we have the architectures where our applications are ephemeral. We try to pack them into tiny containers. We try to give them as little resources as possible so we can scale them horizontally, right? So every individual application will get just, I don't know, like a few hundred megabytes of RAM and maybe like half a CPU. And we want to pack them as efficiently in memory as possible and make them also work that way. So this use case is not very well served by typical Java runtimes, because the JVM is targeted and it's tweaked for having this warm-up curve, collecting information, and then eventually being the most efficient it can be, which is not the most appropriate performance profile when we talk about the containers, where we don't give any resources, and then where the lifetime of the application is near seconds, because maybe you just spin up the container to in response to the traffic load, and then you compute a couple of requests, and then you just kill the containers, and your application, well, goes away, right? So it loses all the information that it gathered, the profile and everything. So you spend resources twice. First, you need to initialize the JIT and all those infrastructure to actually compile and what makes JVM fast, and then you actually don't use the result, which is unfortunate. So GraalVM gives you so there is this trade-off in how we talk about performance, right? On one hand, you have the typical JVM workloads where you want peak throughput, where you want it to be as fast as possible at runtime after everything stabilizes and compiles. And the other part is where you want the memory footprint to be as small as possible to pack it efficiently, and when you want it to be ready to start serving you business requests as soon as it starts up, so sort the startup speed and the warm-up curve. Those two different use cases are served perfectly by running in the JIT mode or running in the ahead-of-time compilation mode. So yeah, the ahead-of-time compiler could be, like, it can't do as many speculative decisions as the JIT can. So it generates more conservative code. So it probably will be like it probably won't be faster than the warm-up JIT. But at the same time, it could be sort of comparable. And on the short-running workloads, it can absolutely beat the JIT by a mile. And it also will excel at those particular dimensions of performance which really are good for the cloud: startup speed, memory footprint, packaging size. The good thing is, as I said, GraalVM offers you both, right? So the application that you run with the JIT, you can convert and run in the ahead-of-time compilation mode. And then you will be able to run them in with very small heaps, and they will run very fast. So normally in the cloud, there are diminishing returns, as in going smaller and smaller, because there are usually steps, right? How you get paid. For example, in the typical serverless frameworks, you will get paid by the memory that you use by the time, and there is a certain step. So like the smaller container, like for the serverless, for the AWS Lambda, for example, I think is 128 megabytes, and the billing is by 100 milliseconds. So like it doesn't matter if you go lower, you will still pay that basic price. So if you get the numbers which are good for that environment, then you're good to go, right? So here you have a screenshot of a small application. We're going to run that in a bit for real, and you can see that you can run with a small memory heap, and it starts in like 70 milliseconds, which is very well under 100. So good to go, right? You can package in the smaller containers. How this happens is native image technology. It takes your application, it takes all the Java classes that you will ever run in the application, and it will take the GC and runtime components from the GraalVM project called Substrate VM, and it will initialize the application, and it will find the reachable code and objects that you have on your heap, and it will compile the code, and it will write out the objects that are initialized, and it will put that all in an executable. Right, so this process takes a little bit of time, a few minutes, that it needs to crunch your application, all the dependencies that you have. It needs to crunch the JDK classes that you're using. It needs to bake in the GC. So, and it needs to initialize all that. So, but when you write out the result will be ready to do useful work as soon as it starts. It operates under the closed world assumption, which means that it needs to see, the native image utility needs to see all the classes that will ever be run when it builds the executable for you. It can also build a shared library, but we'll call it executable, right? So it needs to see all the bytecodes. First, because that enables you to run the aggressive AT optimizations. For example, if you know that your class hierarchy will not change, you know that you can inline certain things, or you can write out the direct method calls, right? If your class hierarchy can change at runtime, then you can just inline and say, oh, my method do something is that direct method in that class, because there could be some classes that extend that, for example. So it gives you optimization opportunities, and it also gives you the opportunity to remove everything unnecessary. If there are classes that are not used, or methods or fields that are not used, it can just remove those, because it knows that all the bytecode is here. It can analyze that. It can figure out, aha, this method is not used. Let's not compile that. And it also allows you to remove the JIT compilation facilities at runtime, or any bytecode interpretation facilities at runtime, because you've seen all the code before and you can pile it all. So you don't have to start up the JIT. You don't have to start the bytecode verifier. You don't need class loaders. You don't need the interpreter for the bytecode. You can save on that infrastructure layer quite a bit, which is what we want, because we don't want to allocate memory and resources for that. The downside of that, right, the trade-off with this, is that the dynamic parts of the language require configuration. If there is something that needs to be absolutely dynamic, right, where, for example, the static analyzer cannot see through your code, it needs help. For example, the most notorious example is reflection, right? People often say that GraalVM doesn't support reflection, which is not true. It supports reflection very well, but the static analyzer cannot see through that. So it needs a configuration file that says, I'm going to use those classes and those packages through reflection. How do you generate that configuration? It's not just reflection, right? You need proxies, and you need some resource files, and you need everything that is not statically analyzable. You need to configure that. You configure that by a Java agent. You run your application in the JIT mode with a certain Java agent, and you execute the code pass, and the Java agent will record and output the configuration that you have. It will write it out in the file. And then when you build the native image, you can use that file to load that configuration. So that works beautifully. The only general kind of restriction that you have is that you cannot load new classes at runtime, because you are operating under the closed world assumption, which means that if you want to load that, you need to load them during the build generation step, right? During the generation of the native image, you need to load those classes and you need to initialize them if needed. And that's a flexible approach, and it gives you really good results, right? Because AAT mode can cut out the unnecessary parts and limit the memory overhead. It can give you the performance of a native application, but it still runs your normal Java application. So here we have an example of a Micronaut. You can see the blue line here is the memory usage. And the test here is that every second we hit it with one request 4 times. You can see that Micronaut application compiled as an ahead of time compilation mode on the left here uses something like 32 megabytes of RAM here, and it doesn't do almost any work. So the request comes, it uses a little bit of CPU, and then it dies down, right? In the JIT mode, you can see that there is a lot of CPU usage, the red bits here, and they're concentrated near the startup. So the most important part for your cloud, when your application starts up, you want it to do useful work because you normally want to run it in response to traffic, right? When traffic hits, you want to scale your deployment, and then you want to make those new deployment units efficient. You want to make them serve user traffic. But the JVM in the JIT mode and the GraalVM in the JIT mode as well, so because it contains JDK, so it's a normal JVM, it will do quite a bit of initialization in the beginning of your code. And then when the request hit, you can see that second red spike there. That's where the first requests start to come. You need to, the JVM sees new code, and the JVM sees that it needs to compile new classes, and it starts doing that. So that takes CPU. And of course, the memory usage also spikes up there. And can you use it? Absolutely, yes. There are a number of frameworks that support GraalVM native image, including Helidon, including Micronaut, including Quarkus, including Pico CLI, which is an absolutely excellent choice for the command line applications written in Java. I cannot recommend that enough. Also including Spring, right? So currently there is quite a bit of work happening to make Spring applications, Spring Boot applications, work as GraalVM native images. And there is quite a bit of progress. If you haven't seen and you haven't looked into that recently, I would absolutely recommend you to look at the presentation by Sebastian Deluza and Andy Clement, which are 2 of the main developers on the Pivotal side that work on the Spring Boot native applications. And in that session, they describe the work that has been done, the progress that has been achieved, and how you can think about like what you need to understand when you try to run your Spring applications as native images. So I think it's a very useful session to look at. And the Spring support, of course, it will come, right? Eventually, Spring applications will work absolutely beautifully. Even now, there are a number of starters and a number of applications that run, but you need to maybe tweak things here and there. And the larger Spring ecosystem, which is a very large ecosystem, is not yet ready for this, right? It's very easy if you start from scratch, if you don't have to support like a lot of existing applications, and it's a little bit harder when you have size that you move a little bit slower. But Spring will come. There is no doubt in that. So another framework that I can recommend and which takes a very interesting approach is Micronaut. So Micronaut is a framework for microservices and serverless computing. It's a complete application framework. It does dependency injection, it does aspect orientation, it does configuration management, it does ability introspection, it does everything. And the most incredible aspect of Micronaut is that it does use annotation processing and Java annotation processors to compute certain aspects of your application at the compilation step. When you compile your Java sources to the bytecode, right, even before any native image can do its work, right, it compiles and outputs additional classes that do parts of the application initialization that some frameworks might do at runtime. It does that at the compilation step. And it's the annotation processing, so it's completely separated from your bytecode, right? So it works from your sources during the build step. So it's after that the application is packaged in the jar and it's ready to go, right? So this is very interesting, and I recommend you to look at Micronaut in more detail. And I want you to show a demo. We still have time. I want to show a demo of the Micronaut application, and I want to build a couple of native images out of that, and I want to talk to you about how you can make them more efficient. So I'm going to quickly go into my VS Code here, and you can see I have my Micronaut application here on the left. It's a very simple application. In fact, it's a sample application that I enhanced with a single controller, right? And this controller, what it does, it calculates prime numbers. Very important business task to calculate prime numbers, right? So we bind that controller to the URL, and then we just want to have this method that will generate our random sequence of prime numbers up until an upper bound. So what we do, we will take the random to and from two indexes, and then we will compute the prime sequence. We will compute the prime sequence here between those two indexes, and we will do that in a not the most efficient manner, but it doesn't matter because this is just generating and simulating the business logic. We'll create a stream and we'll filter all the prime numbers and we'll collect. And to filter, we will create another stream from 2 up until the reasonably bound, and we'll match every number that is divisible by the counter number, right? Which is like our argument is divisible by. So prime numbers. School math, nothing super exciting, but it will generate some data and it will generate some garbage. It will generate objects here for the stream. It will generate objects here for the stream. So on every request, we will generate some data. And then this is very important, and which is very useful. And then we'll render this. How do I build this? This is the Gradle project. So I build this normally, right? I build this normally, and I have my machine here, which is where I'm building this. Right? It's a cloud machine, and it's a sort of decent laptop, right? It has what 16 threads, and it has like 100 gigabytes of RAM, which is very important, very useful. I cannot recommend this enough as well. Like if you have your laptop that does something and you have some computational tasks, just offload them to the cloud. Right. So how do I build this application here? I can build this with Gradle W build. And it will create me a jar file in the build libraries. Primes a cool jar file, right? So this is a normal jar file. You can see I built it just yesterday, and I can run it with my Java. Java version? So my Java is actually GraalVM built here, right? So I can run this, and I can run Java -jar, and I can run this jar file. Very simple. It will start. It starts reasonably fast. It starts less than a second, and it can run this. And you can see also that I can run my application. I will call primes random under 100, right? And I can just see that if I refresh this, it starts and it gives me a random slice of the primes between those under 100, right? So, and those actually are, like if you can see, like 10 here, right? Wait, 10, right? Those are actually primes under 10, right? So it works. And now I can build a native image out of it. How do I do this? How do I build a native image? Very simple. I have a script here, and what it does the build, and then it uses the native image utility, which is also in my class path, right? Which is, if I stop this and I do which native image, it's the native image that sits in my JDK, in my GraalVM, native image minus version. You can see that it's still the same version, and it will just run this, and it will just pass the class path. Micronaut takes a little bit of configuration on itself, and Micronaut runs and prepares your application. So you can literally take the Micronaut application jar file, feed it into the native image, and you get the application back. And I'm going to run this. So build native image sh. Let me just open the terminal here. Wait, what? lol. Wait, opening terminal. This is just simpler here because it's all in one thing. So I'm on the same server and I will do bin build native image. I will run it. It will take just a few moments, right? While it runs, it needs to start the Gradle, it needs to start your application and everything. I'm going to show you what we're going to build next, right? So after building the native image, one thing that you can do is you can use the G1GC based GC to bake into the native image. Remember when I said that there are the components, the runtime components that come from the GraalVM project? What you can do is you can use the low latency GC here. It's a feature of the GraalVM Enterprise Edition, but that doesn't matter. You can use it. You can use it here. What it will do, it will bake a different GC algorithm into your application. What G1GC is good at, it is adaptive, right? So when you run your application normally, and by default, it will use the sort of a serial generational scavenger with the young generation and the old generation, and the objects promoted from young generation to the old generation, right? And then the young generation GC is a separate thing, and the old generation GC is a separate thing. But there are like fixed sizes for those generations. It's very simple. It's very efficient because it doesn't do a lot when your application is actually running. It just only does work mostly when the application needs to GC. G1GC is working differently, right? It runs in parallel with your application. So it incurs a little bit of a throughput hit towards that, but it's adaptive. So it splits your application memory into like smaller regions, right? And then it can grow young generation sizes and old generation sizes independently, which is very, very useful. Very useful. So if you want an adaptive GC for your workloads, you can use that. And then one very important thing that you can also do on top of this thing is still inlines and computes here. It's supposed to be a minute. I'm not sure how much time it has passed, but I want you to show this additional example. Let me just make this smaller, right? How do you use profile guided optimization? Profile guided optimizations is when you build an instrumented native image and then you apply workload to it and you make it record the profile, sort of like the JIT will use when you run in the JIT mode, right? But it will output that to a file, and then you can use that file to build the more optimized native image that takes that profile into account and is more faster and more efficient. So this is a more involved script here, right? So we're gonna use the same native image script before, but we'll supply the PGO instrument parameter. Then we will apply load, and we're gonna look at this test sh script in a second. We're gonna apply load to that executable that we got there, and we will record the profile files, and we can apply load more, and we can record a different profile, for example, and then we can build it and give those profiles to the application, to the native image utility. So it will build here, and then it will build us the final optimized executable here. So now our native image build here succeeded. Look, it took what, 2 minutes? It took 2 minutes here, but it gave us the executable. So let me make this larger, because now I want this to be the center of attention. Let's go here. This is better, right? If I do ls to the primes everything, right? You can see that our application is 70 megabytes. 70 megabytes, and then the G1GC one is a little bit larger. The WIS PGO is a little bit smaller. The thing is, this is a standalone executable that is self-contained, so you don't need the JVM to run it. What's important here, you can also use the utility called UPX. Help, and the UPX utility can compress your executables further. So you can run it on your application or your native image application, and you can get good results and compress it even further. So what we can do, we can run this, right? We can run this application. It will start beautifully in 20 milliseconds. The native application startup times ridiculous, and we can still see that the application works the same way, right? If we do 100 here, it just gives us 100. If we do 1,000 here, it will give us 1,000. You can see that it's actually very snappy. And the same way, I will be able to start other applications here as well. So that was serial. If we do primes G1, right, it starts very fast and it will still be working. If we do primes G1 PGO, it starts very fast. So in the startup, there is no much difference here because they all start very fast. But at runtime, there is quite some differences. So now I want to look at the test script that we had there, right? Bin test sh. And this is the script that will do the following, right? Go away. This will do the following. So we will run our application that will pass the command to run it. We will run it. We'll use the PS record utility to record the data about CPU and RAM usage for that. And we will apply the load using the hey load generation tool. And we'll apply load for half a minute on a certain URL, which would this our business logic, and we will record the numbers and we'll see what it gives us. So I'm gonna run this, and I'm gonna run this using the following. Wait, I'm gonna copy. There is a script here that I had before. So run all tests. I'm gonna run this with the serial thing here, right? We are running the serial mode, the tag. We are gonna hit this URL and we say that we want to run prime serial, and we give it 256 megabytes of RAM because we want to limit that, because you want to give your containers less RAM. So now it's gonna hit this for 30 seconds, and which is very good because we have like 3 minutes of the session here remaining. So 30 seconds is enough. And I want you to look at one number there. We're going to run this experiment 3 times. We're going to run this serial, which is the normal native image that we have. We're going to run the PGO optimized one, so the best one that we can get. And we're going to run this using normal JDK, right? So the numbers that we want to record here is this. It served 5,000 requests per second for 30 seconds, right? So this is what, 150,000 requests, which is quite a bit of time, quite a bit of requests that we wanted to serve. It was very fast normally. There was something was canceled here, probably at the end of this thing, but 5,000 requests, right? If I will run the same thing for PGO, right? All the PGO, the latest one, also 256 megabytes, but I will just run the optimized native image here. It will do exactly the same things, and you can see that just when I clicked, it very quickly got to the startup and very quickly got to the load generation thing. So we're gonna see the numbers, and the numbers will be much more spectacular. The main reason for that is that G1GC is adaptive, and this workload, this specific workload, which is sort of how normally web application workloads work, generates quite a bit of garbage on every request, right? We've talked about how the streams for calculating param numbers will generate objects and will generate garbage. So the G1GC, which is adaptive, can make your when your young generation much larger. And look, it runs and it serves 15,000 requests per second, right? I will just run normal Java as well. I took Java 11 because it features G1GC. So the benefits here is mostly G1GC, right? It was adaptive, so it could enlarge the young generation, so it didn't do as much GC. But PGO also helped. If I run this with Java, you can see first it starts up a little bit longer. This is Java 11. A random Java 11 distribution from SDKman. And then I'm going to run that. While this runs for 30 seconds, let me just finish with a few slides, because I wanted to finish with the few slides before this, playing the slideshow window, right? The key performance improvements, how you use the new GC, you use PGO, you can configure memory with XMN normally, so you can package it in smaller things. You want to minimize the container size to throughput ratio, so the memory usage to throughput. You want to write small methods, but in general, if you want to run with the best throughput, use GraalVM JIT. And if you want best startup and footprint, use native images. So that was GraalVM for Java workloads. There is very many different ways how GraalVM can help Java developers, most normally by improving performance of their Java applications. You can look into the Oracle GraalVM Enterprise Edition if you want. It gives you even higher performance, but the Community Edition is functional equivalent. It can run the same applications the Enterprise Edition can. So there is no like vendor lock-in there. And it's production ready. You can download that. You can, if you have any feature requests, you can go up to our GitHub. You can subscribe to our Twitter feed, find our blogs and everything, and you can participate in the GraalVM community. So while all this said and done, let's see the results for the JDK. JDK got a much more requests in the half a second, like more performant, but it also took way more memory, I think. Was it? Did it take more memory? Right. So this is unexpected. Yesterday I had a different result. Anyway, you can run the same application on JDK, and you can run the same application on native image micronaut applications very nicely. Right. I'm out of time here. I'm sorry for the very scrambled finish of this presentation, but GraalVM is very exciting. I hope you looked at what it can do. I hope you looked at the optimizing the native image as well a little bit with the script. If you have any questions, you can just ping me somewhere. Right, we have some few questions in the chat.
So first one is, how did you generate the graphs, the difference between ahead of time and JIT?
Yes, so very quickly I can go through that. So it's a PS record utility, which you can install. It's a Python package. So you just do pip install PS record, and it will download things. It uses a matplotlib, and it will be able to generate you when you do like PS record and you just pip this command, right? It will produce you the results like here. Let's take the latest G1, GC1, right? It will produce you the results like this. This is our runtime here, right? Or the latest JDK 11. I think this is the latest. You can see it produces the similar results, right? For our half a second. And so that's how I generated those graphs. And I had the test with just 1 request, 2 requests, 3 requests. Right?
Thanks. The next question is the native image built independent of the JDK? Don't we need to use the no fallback option?
Can we use Right, so native image is built in the context of the GraalVM distribution that you're using. So it uses the JDK runtime library classes from there, right? Obviously, when you use Java-lang string or something, that implementation needs to come from somewhere. It also currently bakes in the implementation of the native methods from the JDK library. So it's sort of not independent of the JDK. It uses the GraalVM distribution that you currently are using. Don't we need to use the no fallback option? The no fallback option, there is an ability for the native image to build, like if it encounters something not configured properly, it will fall back and it will just produce you an executable while it has the classes and hotspot together in one file, right? So it will run on the normal hotspot normally. If you want to disable that behavior, you can use no fallback option, but it also you don't have to. So with micronaut applications, I know that they build perfectly for the native image, right? So I just don't need to specify that, and my application is a native image, not just hotspot baked in. And can you use low latency GC with CE? Any alternatives? Currently, the G1 GC based GC is the GraalVM Enterprise Edition feature, so it is only available there. So you use the normal serial GC with the Community Edition. You can tweak it for your particular workload. For example, for this workload, if I increase the young generation size considerably, I can get a much better performance out of the GraalVM CE as well. But the G1 GC is just, it's adaptive, so it does it for me automatically. And of course, it's a GraalVM Community Edition is the open source project. So if you are a GC enthusiast and a professional, you can contribute a different GC there. You can also like, there is a cool option. You can also configure your GC in a way that it never does GC, kind of like Epsilon GC. But you need just to configure it that to never do any collection. Serial GC can do that, right? So that's that.
Okay, thanks for the answers and for the whole presentation.
Right. Yeah. Sorry, a bit run over time, I think, but
no worries. We still have 3 minutes till the next
until
session.
the next one. Excellent. Thank you very much.